Okay, welcome. Thanks for coming to my final presentation for MSME. Today I'm going to be talking to you about my project, Environmentally Adaptive Cruise Control and Autonomous Vehicles that imitate human behavior. Okay, so some background and motivation for this project really stems from the current autonomous vehicles that are on today's roads. The current autonomous vehicles don't take into consideration the psychology or the human factor to driving on the road. The robots are usually very objective based and they will meet those performances at all costs, not considering the comfort of their driving trajectory. The driving trajectory of level two and level three autonomous vehicles are currently unoptimized and not trusted by passengers. So some work to try to help quantify these passenger feelings and psychology while driving inside of a car have been conducted by Peng and others from the institute in China. And their study aimed to introduce a method to assess the relationship between driving behavior and passenger comfort. The research gathered subjective comfort ratings from passengers exposed to various types of driving styles. They measured physiological responses, specifically skin conductive response sensor, as seen in Figure 1A, and a heart rate variability sensor, which served as indicators for stress and comfort levels. So they developed a model of what they thought that would be an uncomfortable driving trajectory. And they also asked the participants to grade whether or not it was aggressive or not aggressive. So from this, they were able to create a matrix comparing the two, both predicted and professed from the passenger, and they were able to come up with a probability matrix that verified their model. This study wasn't very accurate, as they only achieved about a 50 or 60% rating from their model, but it did highlight the fact of what made a driving trajectory comfortable and uncomfortable. So some work that has been done to personalize an autonomous vehicle control was done by Mirabilo and others from universities in France, where they sought out to create a personal adaptive cruise control that kept a certain speed throughout in traffic. The personal adaptive cruise control was able to learn and replicate individual driving behaviors, ultimately offering a more personalized driving experience. The study approached the problem using an IRL, which is an inverse reinforcement learning model, to find a weighted cost function, ultimately to implement into a real controller, which was a nonlinear model predictive controller. The IRL recovered a unique weighted vector that was learned from a sum of features, including acceleration, desired speed, and safe following distances from the person driving the car. The IRL derived function was then it acted as the objective function for the NNPC, optimizing a minimum gap distance and bounding acceleration and speed. They were able to verify their model with using the root mean squared error for the position and speed deviation from predicted and actual trajectory to evaluate their performance. So when actually implementing these control models inside a real vehicle, there needs to be a series of sensors that gather this information. And usually one sensor doesn't do enough, so there needs to be some framework. So some work has been done to build this optimal framework by Jaromi and others from the University of Illinois in Chicago, where they address the critical need for efficient and reliable perception systems in autonomous vehicles, combining multiple sensors in a fusion framework that enhances the vehicle's ability to understand and navigate its way through the environment safely. They studied the study identified the weak points of the sensors. They saw that LiDAR was really weak in varying weather conditions like rain and snow, and cameras were weak in extreme lighting conditions. They also saw that radar had a low resolution for spatial understanding. So usually where one sensor fails, another one picks up, and that's the beauty of the multi-sensor fusion framework, is that the combination of these sensors can give you a good picture of what's going on around. So they saw that the LiDAR picked up where the radar had failed, and it enhanced spatial accuracy, where the radar was really good in actually detecting the object in a specific direction where the LiDAR couldn't. The camera was good during the day, not so much at night or during varying weather conditions, but the camera was good when all conditions were optimal. Yeah, and this study also demonstrated the superior performance for object detection through LiDAR and radar. Okay, so when actually implementing these data acquisition or implementing the data acquisition in systems or computers, there needs to be some type of optimization for data. Yeah. So one of these methods for calculating this data acquisition is a process called multi-threading or multi-core, and what it does is it allocates different processes to different cores on the CPU, allowing the processes to not be conflicted by different computational processes. So yeah, and so the work was done on this by Arthur and Lorenzon, where they studied how different multi-threading application program interfaces influence the performance and the energy consumption on embedded systems like a Raspberry Pi. They utilized a multi-threading API, which enabled different levers of the CPU's cores to execute separate tasks together, or separately, but at the same time, in real time, which ultimately resulted in faster overall performance. They found that by carefully selecting multi-threading APIs and optimizing the synchronization points for the multi-threading processes, they were able to achieve significant performance gains while minimizing the energy consumption, highlighting the importance of efficient parallelization strategies. So another study that is particularly important or to this project is a study that was done by Bashash and Kamahani, where they implemented and studied a supervisory lateral slip prevention controller on an autonomous vehicle. And the study develops an integrated control systems for maneuvering and slip prevention of an autonomous vehicle on curvy roads. And it also implements a longitudinal control system for design. A longitudinal control system they designed was able to keep corner speed, while lateral control system was designed to maintain the lane. The steering angle was limited to a relative speed curvature, but this assumes that that information was available. The curvature of the road was able to be calculated. Okay, so moving on to my project and how I'm going to implement these control principles inside of a small-scale RC car. It's important to actually build the test bed first. And so the way that I did this was I scaled the parameters from my car down from the average truck in America, which ended up being a F-150. So I took the dimensions of F-150. I took the dimensions of its wheelbase and its total width. and while also taking the average dimension for the road width. And with these parameters, I can get a ratio of how much space the car takes up within the lane, and I can apply that same ratio to find out the best or the same or not, yeah, define the road width of my test setup. And so by doing this, I took the ratio and I divided it. I divided my test vehicle width by this to find the road width, which ended up being around 215 millimeters. So now that I have the actual road width, I'm able to create the road and simulate the vehicle dynamics that were generated and derived by Kambahani and Bashaj in their paper. And they ended up using a simplified kinematic bicycle model, which breaks the car up into two wheels instead of four. And from this, they derived a optimal lateral control. And the only difference between mine and their control law was that I added a KI where they didn't. And this was to ensure optimal tracking performance. I also added a steering limit to the calculated lateral control angle, which was 30 degrees, and this ensured smooth convergence of the to the set point on the road, preventing jerky steering input behaviors that would make a passenger uncomfortable. Furthermore, I added a recursive weighted averaging filter that filtered out all of the high noise from the calculated steering angle, and this was tuned, as you'll see in the next slides, to minimize the noise, but also optimize the convergence of the vehicle to the center of the road. I also had a longitudinal control, which calculates the curvature of the road. And if the curvature of the road is exceeded based on a predefined, like, is it the curvature of the road is exceeded, then I will decrease the speed in a proportional manner. And this speed is also tuned to ensure that the car doesn't fluctuate back and forth. It doesn't speed up or slow down too fast. So analyzing the car performance on the Z road, I looked at three different metrics. One of the metrics was the positional deviation from the center line, making sure that that doesn't go or exceed above 15%. I also looked at the steering input versus the distance traveled on the road, making sure that I don't have these big fluctuations near the steering limit, while also looking at how fast or how much turning that the vehicle is doing as it's turning on the road. So is it going back and forth between the line, or does it go really hard over the line and then come back and then converge to the center line? I also looked at speed control versus distance to ensure that the car doesn't accelerate too fast. And so in order to make sense of these values, because they're so small and scaled down, I added a scaling factor from the F-150, and I found the scaling factor from the F-150 in my car to find what speed the F-150 would have been if it had been put through the simulation. And so on the low end, started around 20 miles per hour, and on the higher end of the speed, which was 27 miles per hour. And I found that to be reasonable to, so it was about a 7 mile per hour increase over 1 meters, but if you scale it up by 36, that's a large distance to accrue 7 miles per hour, and it wouldn't be felt by the passengers substantially. So there's what I was talking about with alpha adjusting it itself. So you see with a lower value of alpha, you're filtering it a lot more, which is delaying the system. But reducing that high frequency noise. So at first I thought that this was going to be good, but I looked on the later end of the half of the road uh, dynamics, and if I was in a car, I know that I would be thinking someone is the driver can't drive because he's just going back and forth between the center of the road, and so led to increasing the alpha value to increase my convergence time. So here's the performance on the sign road. Same thing as before. The speed control goes from 20 miles an hour to 29 miles an hour very sharply. And this is due to the initial straight line or the straight segment of the road before it actually goes into the sign pattern. And that is typically normal in like a regular driving situation where you will see like you're going a set speed um, and you so yeah, so you're not going to be driving slow on a road that is straight and not curvy. You're not going to be taking into that into account. But you could also see how it doesn't speed up in the later segments when the road is curving. So here's also the different values of alpha. When it increases, it will decrease the high resolution noise, leading to a faster conversion time. Okay, so moving on, a little bit about my system hardware. I'm going to be using a Sunfounder PiCar X, which is equipped with two 6-volt DC motors. It's also going to be powered by Raspberry Pi 4 Model B. It has a Pi hat that comes with the car, and this Pi hat is essentially a breakout board that allows you to connect various types of sensors to it. The car is going to be powered by two 1860/50 rechargeable batteries, and the car also has a IMU for the observer control, as we'll see in the next coming slides. So during testing, I did have a lot of thermal problems. So I needed to make some heat thermal management system so that I can continue to run my tests, because as the CPU got hot, the computational speed started to hinder. So a couple of things that I did was I added a fan, 5-volt PWM fan, and I added a variable fixture to it. The variable fixture helped me design it or implement it really quick, because it allowed me to adjust it forward and back and side to side. This was very important because I knew that I was getting pretty close to the IMU, and the fan vibrates, and that would induce more noise than wanted, or yeah, it would induce a lot of noise in the IMU, which would skew my velocity results. I also had to extend the Pi hat above to increase the or the heat cooling channel, so that heat can be extracted from the CPU, while also adding a heat sink on the top of the CPU. Okay, so going into the data acquisition portion of the project, in order to implement lateral control, it's important to understand where the center of the road is. And so the center of the road is calculated using the OpenCV library, but at the core of it, it's calculated using color contrast in the frame, in the picture frame. And so this is done by masking all of the colors that aren't specified into a black pixels, and letting the colors that are specified into white pixels. And so this is done through the HSV color space, which allows variation for colors to be allowed in that masking process or the filtering process. If you can see on figure 21, even though the road is green, the light shining on top of it is reflecting off of that green, which makes it look white. So the HSV allows that saturated value or the less saturated value to be processed by OpenCV. And so this was a continuous tuning process that I had to do as I switched between different environments and different colors because of the lighting and the problems with image processing. So in figure 23 and figure 25, you can see what it looks like when there's bad data or bad filtering from the OpenCV detection. Okay, so moving forward, um, once the proper color masking is completed, as seen in 27, a Gaussian filter is applied. And what the Gaussian filter does is it blurs all of the contours that are the Gaussian. It blurs all of the pixels that are detected to create a steeper gradient of the pixel intensity, which allows edges to be more or to be further or yeah to be precisely detected and processed. Both of these processes are computationally demanding, so it's going to be of mind when in the future, uh, whenever we run tests. So after this process is done, we have to segment the actual frames, and by doing this, we just tell the camera to look at a certain region of the lane and do its filtering, its masking process. And then after we have our selected region of contours, we can use OpenCV's image moments to calculate the center. And so this concept was kind of hard for me to understand at first, and I'll try to explain it. But image moments is a mathematical summary of image shapes and pixel intensity distribution. So if you have let's just say you have a 1 by 1 square, and all of your pixels in that square are one or intents of one, you can mark each pixel in that 1 by 1 square as one that is of intensity value 1. And if it's not, then you basically label it 0. And so for each X coordinate that has intensity, we'll give it a 1. And for each Y label that has an intensity 1, we'll give it a 1. And so we do this all the way across the contour that's actually detected. And this helps map out the actual contour in pixels. Because you can see in figure 27, it's not an exactly straight line. It's converging into the middle of the frame. And so we get the X moment, and then we get the Y moment of the contour, and we get the whole area moment, and we can find the X and Y coordinates by dividing each moment by the area. So that's kind of what you see in the right. OpenCV makes it really easy. About 4 or 5 lines of code. They'll take the whole moment of the contour, and they'll put it into an array that you can call and simply divide to find the center of your lane. So in the previous process, what was done was segmentation of the frame. So I took regions of interest for each dashed line on the left to calculate the midpoint of each dashed line on the left, as well as calculating its corresponding x-axis midpoint from the contour on the right. So once I have these midpoints from the left contour and the right contour, I can then connect a line between both of them to get a midpoint. And the midpoint is going to be representative of the center of the road. And so as I do this along all of the contours, I get these series of midpoints. And these series of midpoints can be connected using a polyfit line, or fitting the line with a polynomial equation. And it gives me the trajectory of the actual road. Now, when I was first doing this and debugging this process, I saw that the midpoint calculation was just really noisy. So I took the furthest midpoint calculated and the closest midpoint calculated, and I averaged them together to get a singular midpoint from that line.
Sorry,
That's what
Anthony. How many slides do you have still?
uh
What's
yeah,
the
I'm
number?
watching time. I'm watching time.
No, I just want to
Yeah.
give you like what's the number of this slide?
Mm, I don't know.
So
Oh,
you
18.
have about, yeah, try to wrap up
Yeah, I'm
in,
about halfway.
yeah, so try to be faster.
Okay, sounds good.
Yeah, you have about 15 minutes.
Got it.
Okay.
Okay. Okay, where was I? Oh no. Oh, it's lagging now. Sorry.
Okay.
Okay.
Yeah.
So obviously this didn't work, so I switched my method up to going to a center line. So same methodology as before. I'm going to calculate the midpoint of the center for a region of interest. But I'm going to fix the actual y pixel to uh, the calculation to a singular y pixel, and that y pixel would be 150. And that helps because if something was in the middle of the road, it's going to break up. Uh, it would break that contour up. It would, yeah, break that contour up, and then your moments would be calculating two different types of set points, which would be really noisy. So yeah. Um, so in order to calculate 15% lane deviation or measure that, I need to get the real world dimension um, through in pixels. And so you do this through a process called prospective projection, which is a trigonometric relation of real world dimensions and pixels governed by the camera's field of view. So W real is what we know. That's 215 millimeters. And we find W pixels, which is that distance represented in pixels with a measured distance um, in real life. And so what I did was I placed the car at the very beginning of the road. I put a ruler on that line segment, and I placed a screwdriver on the ruler, but at the same time positioning it to the center of the line. And so using the ruler, I found out that I was about 111.5 millimeters, and I entered that distance into this calculation, which gave me 15%. Or which gave me. Oh, I sorry. I entered that into the equation, which gave me 215 millimeters relation road relation in pixels. So 215 millimeters equals 513 pixels, and I multiply that by 15, uh, which was 76. And so I had to make sure that my car position didn't exceed 76 pixels from the road center. So moving on to longitudinal control, the estimated the velocity is used by an observer-based approach. They measures motor input voltage and the IMU output. The voltage was measured by ADS 115, which is an ADC. The voltage divider was enabled the ADC to use the FPG gain of 8, which increased the resolution. And as I go forward in testing this, I need to make sure to tune L for the observer to ensure convergence, while also choosing the time step for the observer dynamics low enough to where it doesn't alias any of the values, but also remains fast enough to capture the dynamics. So the ways that I'm controlling the motors is through pre-existing libraries made by Sunfounder that interfaces the motors with simple functions called in Python. I shouldn't say MATLAB. All motors controlled by a PWM signal, the servos and the DC motors. The input for the servos was plus or minus 90 degrees, which needed to be calibrated, and the input drive motors was plus or minus 100, with 100 being 100 forward and 0 being dead, and then 100 negative or negative 100 being the reverse direction. So the data acquisition for object detection was completed by both an ultrasonic and image processing. The image processing object detection was done around the TF Lite, which is a lightweight version of of TensorFlow, which enabled um, MobileNet V2 and the Cocoa dataset to be used to actually detect real images. Um, this was really challenging to run this type of object detection on the Raspberry Pi because right when I started to apply the motor speed on the road, the video would just fail altogether. And after further research, this error is a voltage power. It's a power supply issue. So the Raspberry Pi is going to limp mode, trying to conserve power so that it could run. So basically, ultrasonic was used for this project for for object detection, which gave me a plus or minus 180 centimeters distance to detect something. So by testing the longitudinal control, I had it set up on a straight line. I had marked zero point 0.5 meters to measure at different lengths. Um, and I ran the test at 50 PWM. So the expected velocity that I'm going to be measuring against the estimated velocity was done the previous semester where I integrated the IMU values across the similar test. So I have an expected velocity for each PWM value. So here's what the test would look like. I go ahead, start this code. It's also running a PID control for lane following. And there's the observer in the background calculating the velocity, but at the same time, it's multiplying it by each time step to get a measured distance. I then take this distance and compare it to the expected velocity times the time that it took for the test, and I get these results. So in the left, you could see that test being ran. After a long period of time, you start to see it converge. But a very weird thing that happened, and I think it's because of the expected velocity and then not taking into account. Sorry. The that big surge you see is from a noisy IMU data reading, and the velocity or the observer can't really calculate for that because it's an inherent feature of the of acceleration. You get this very big spike in accelerometer values, but as time goes on, you start to see it converge, and that really comes from the tuning of the L value and tuning of the tau value, because the tau value that was used was the average between all PWMs. It wasn't 450 PWM. So that can also affect it. This was a second test done for longitudinal for 2.5. You could see 20% error, 10% error. Yeah, still a bit noisy. So setting up the lateral control. The way that I tested this out was creating the same road that I did on MATLAB, but in real life. I only had a ruler, so I had to convert it back into feet and inches and individually mark out the points that MATLAB had created. I'm using shades to block out the environment for potential noise uh, from the camera to read. So you're cleaning up the data coming in for the image processing. And so this is the first test on the Z road with 38 PWM. So I tested two roads with two speeds, and we will see how that goes. So the car really struggles during the turns, and a couple of things lead me to believe this to be. If we look at the portion of the actual turn segment, the controller just reacts way too late. There's no, and this makes me believe that the processing of the frame is a lot slower than the dynamics of, or the speed of the vehicle, which, I mean, just results in a delayed control input. I mean, you can see this in the data as well. I've created 4x4, one measuring the steering angle, one measuring the vehicle speed, one measuring the air of or the positional error within the lane, and then the last is the PWM input, which is how much it's controlling the speed essentially. But on that first segment, you see about a 35% overshoot. But on the second segment, you see close to that 15% target that we are searching for. And then now going to the 48 PWM, you're going to see an this exaggerated dynamic. So even more overshoot and less steady state or more steady state air. So that was the Z road. And then moving on. Oh, so this is the performance. So it's really just staying in between that 35% air oscillating. Um, and the speed convergence also just working to try to stay in between those bounds. So this is the sine wave. So the performance on the first curves for both roads don't do so well. They do better on the second curve. And you'll see that in the data where you see a big overshoot on the first. So in order to get the actual road or in order to get the car running, the stable speed that I have for 38 PWM is actually too low for the car to get going. So I added a boosted speed at the first 1 second of the test to get the car going. So this can explain the overshoot at the very beginning because the vehicle dynamics are too fast for the controller. Or no, I'm sorry, the data acquisition. Oh, the vehicle dynamics are too fast for the data acquisition, and which explains that overshoot. It's reacting too late. It's lagging, and it could also explain the position uh, the better tracking error in the secondary curve. Here's with the 48 PWM. So as time, well, and here are the performances. You see a big overshoot in the first and a little bit less, but nonetheless, it's basically the same actually. And then, yeah, yep. Some improvement for the study is really to improve the data acquisition from the cameras, the observer, and the ultrasonic. I think that they're conflicting with the controller themselves, even with multi-core or even with multi-threading enacted for the observer control. I think a supervisory control or data acquisition will, or method will reduce the system lag. Also for object detection, implement a 2D LiDAR, maybe on a separate controller as well. And then add a low pass filter to the steering angle for the higher speeds. I think that will uh, keep the bounds within, or keep the steering within the bounds required. But yeah, that concludes my project.
Okay, thank you, Anthony. Thank you for your work and presentation. So now we have time for questions from the committee. Dr. Furman and Dr. Hamad, you can start.
Yeah, so Anthony, it looked like on that um, S curve or Z curve,
Mhm.
you worked out that offset that you had shown me before. Is that right?
Yeah,
What
yeah,
happened?
yeah,
What did you find was causing that?
yeah. So before when I showed you, I'd never even had. So Bashash, he had a well, there's two things. One, I made the road a lot smaller, like you had suggested, not with a less sharper curve. And then two, the rate of change of the curve was not implemented inside of the lateral control, and that was like basically Bashash and Kamahani's major um, like that's what they did was they built the supervisory lateral control that detected the rate of change of the curve. And so that helped a lot, as well as adding that filter. That filter dampened out a lot of the vehicle dynamics through the curve.
Okay, good. But it looked a lot better.
Yeah.
Yeah, looks good. So I just had one question on the last slide you mentioned. One of the things that you could do is increase the observer accuracy. How would you go about doing that?
Yeah, so I what I think is happening is it's conflicting. I'm not so in the observer slide, in practical applications, in order to avoid aliasing, you want frequency to be about 10 times larger than your highest frequency. So right now I'm only doing about 8 times, and I think that with by decreasing the time step, I can get a higher resolution of the observer itself. Um, yes, yeah, yeah.
Okay. All right. Sounds good.
Yeah, and Anthony, what do you think? Like, what do you think that you use Jetson Nano, right?
No, I use Raspberry Pi.
A Raspberry Pi.
Yeah,
Okay. So what kind of microcontroller do you think that would make it better? Like, what do you
yeah,
think?
yeah. Jetson New.
Yeah. Okay.
Yeah, that's like
And
a dedicated microcontroller for.
yeah,
Uh, yeah,
I see.
So you think the real lag was in the image processing?
I do. I do because I tried to speed. So there's a couple things that I try to do. I actually tried to. So the set point is based on that fixed camera position, and you don't want to move that camera because it's calculating your error. So one of the things that I tried to do was move the camera along with the error, compensating for like that position, the position that I'm actually moving. Like I'm deducting the error. I'm at, calculated from the angle of the camera that I'm moving, and it just I don't know. I made it a lot worse. Um, as well, that video I think really drove that point home. Was it was just acting too late, and I tried to speed up the controller, more P, um, and it would just throw the system out of whack. So
Do you know
yeah,
what
it's
the AV car guys do for lane following? I mean, how do they do this? Any of the
um
papers you read?
they yeah, I don't know off the top of my head. I think
Okay.
yeah, it's yeah. I mean, they all use cameras. They all use lidar. They all use lidar for position or object detection, and they use. They don't all use lidar. A lot of them use camera.
Hmm.
Um, yeah, yeah. Not off the top of my head.
Hmm.
And what's your sampling time right now? Like what was the sampling that was
It's
working?
it's 0.0157.
0.015, like 15 millisecond.
Yeah, 15 milliseconds.
And that was like a minimum that you can get to, right?
Yeah, that was a minimum. Yeah.
Okay.
And then the tau was 0.12. That was the average tau. So
What
yeah,
do you mean by tau?
the rise time for or the response time for the motors to reach steady state. So I guess it would be speed. It would be the rise time for speed.
How was it?
So
1.2?
no, it was it was 2.2. 0.2. I forget. Yeah, I think it was 0.2.
Okay.
Eight times of 15. So
So that means so your motor is enough fast and strong. The only issue is just the computation that you have for image processing, right?
right, right. And I think they conflict, right? They're both very computationally heavy. They both depend on that that time step. One for that PID control and the other for the observer control.
Mm-hmm. Yeah, makes sense. Any other question from committee?
Nope.
Okay,
No,
so
I'm all set.
yeah, okay, so um Anthony, if you can just leave the meeting, I will message you on Google to come back and we would have
Yeah.
this discussion
You can
with
put them in a waiting room.
um that's the same. Like, okay, let me see that.